Moving on from industry to university now. And our next speaker is someone who studied electrical engineering at the University of Erlangen-Nuremberg. He later received his PhD in robotics and joined Siemens to work as a system architect in the field of standardization of the Profinet isochronous real-time field bus. In 2006, he was awarded a full professorship at the University of Applied Sciences in Amberg, and he was later appointed as chair of automation technology and robotics. His research interests include various aspects of robotics and virtual commissioning, with a special focus on adaptable factories. Please put your hands together for Professor for Automation Technology and Robotics at the University of Applied Sciences Amberg-Weiden, Professor Dr. Ing. Matthias Wenck. Welcome, Matthias.
Thank you.
Hi, Matthias. Great to have you here with us. Stage is yours.
Yes, thank you, Max, for the introduction. Hello, everyone. I'm happy to be here today to talk to you about smart factories. In my presentation, I would like to give you an idea what smart factory means and how you can transform a conventional production environment to a smart factory. Oops, sorry. Can I go back? Here, okay. Sorry for that. Okay. I will start my presentation with challenges and requirements that you should be aware of. As you all know, there are some current challenges in conventional production environments. The speakers before had talked about this. We have rapidly changing customer requirements, and the individualization of products is increasing. And another important aspect is that the number of variants is also increasing and the lot sizes are reducing. So what can we do? Or what products are we talking about in this context? And for an example, I would like to introduce you to quick connect couplings of our industrial partner Lüdecke from Amberg. And as you can see, these products are manufactured in a wide range of variants. Another important challenge is that such products in this wide range of varieties has to be manufactured cost effective. And this is only possible to realize by increasing the level of variant flexibility in your production environment. So what is required to achieve a high level of variant flexibility? And in this presentation, I would like to give you some ideas what we need. We need a highly flexible material flow, mechatronic adaptability, an autonomous control system, a standardized data model, and standardized data exchange mechanisms. And these topics are characteristic to smart factories. And to give you an idea how to realize a smart factory, I would like to introduce you a research project we have recently carried out. The research project was entitled Development of a Smart Factory for Small Device Assembly, and it was founded by the employers' associations of the metalworking and electrical industries in Bavaria. And we worked together with 9 regional industrial partners on this project. And the first topic we worked on was aspects of mechanical design. In a production that manufactures products in low variance, the sequence of value-added processes is generally in a linear order. As you can see in this animation, the workpieces are moving through all production modules, and the only chance to make some differences is to skip one or more modules. But if you have a production environment with a high degree of variant flexibility, usually the value-added processes are generally not in linear order, as you can here see in this example. So in the first example, you have conventional conveyors. The material flow is only moving in one direction, but in a at a high variance production, you have to realize a multi-directional material flow. That's very important. This is difficult to achieve with conventional conveyors, but robots are optimally suited for this. So we decided to develop a robot-assisted material flow. To ensure multi-directional material flow, we have built up or designed so-called material flow modules. They can be equipped with robots or with rotary indexing tables. The rotary indexing tables are used for material flow branching points. And here you can see how these material flow modules are arranged. They are mechanically connected by a transfer plate, and the transfer plates you can see here between these material flow modules. They can also be used for exchanging the workpiece carriers between two material flow modules, and the arrangement of these modules define the structure of the smart factory. And then value-added modules can be docked on these material flow modules, and all value-added processes are done in these value-added modules. And they can easily be exchanged, though it is possible to achieve a high degree on changeability, which is very important for an adaptable smart factory. And these value-added modules are equipped with articulated robots or with gantry robots, for example. So I come to the next point. Let's have a look on the control technology concept. So it's very important in our project that the control software in each module acts automatically. That's very important by such high flexible production environments. And this leads to a decentralized control concept. And with such a decentralized autonomous control concept, no supervisory control is needed and no cross-module engineering is needed. That's very important because this reduces the engineering effort significantly. But there's another very important topic. We have implemented a service-oriented production approach. What does this mean? In this PLC program of each module, the PLC program provides application-neutral services. These represent the skills of the module, and this module and module-specific control applications call these services to control the automation process. And the important thing with this is that application-specific changes have no influence on the PLC code. That's very important. So I would like to give you a brief example. Here you can see a workpiece carrier, and the workpiece carrier contains a series of data structures with a sequence of skills to be executed in a suitable value-added module. And when the workpiece carrier is put or placed in such a value-added module by a robot, then with an RFID reader, this data structure is read, and a control application can call the needed services to do the value-adding process in this module. This concept is implemented consistently. So also the robot capabilities should be implemented as manufacturer-independent services in the PLC code. And I think everybody in the audience knows how you can realize this, of course, with the standard robot command interface, SRCI. We used it to control the robots in our real smart factory. However, we implemented a real-time robot interpreter in C++ for our virtual commissioning. And with virtual commissioning, we test the PLC control software using a virtual twin. On the other side, we use material flow simulation. And for that purpose, we use technomatics plant simulation. And material flow simulation is very important in the context of smart factories because the biggest challenge at runtime is to avoid deadlocks in the material flow in the real smart factory. And as an example, you can see here a two-dimensional plant simulation module of a smart factory. And you can identify the material flow modules, the transfer plates, the rotary indexing table, the value-added modules, and here some transport modules which supply the smart factory with workpiece carriers. And in this example, a deadlock occurs in the top left-hand corner, as you can see here, and the production stands still. So what to do if you exchange these two value-added modules? That's the only thing you have to do. Then the material flow works without any deadlocks. Here's another simulation. Nothing else has been changed, only exchange of two modules. So you can see a material flow simulation is really essential before a new production order is executed in a smart factory. And it's a really important point to look at. You have to do a material flow simulation to avoid these deadlocks. And the deadlock-free arrangement of the value-added modules can be done manually at engineering, but in future, more and more, there's machine learning used. And this is what we want to do in a follow-up project for an optimized arrangement of these value-added modules. So we come to the next topic, a very important topic, standardized data management. And I think this is one of the most important topics in the context of a smart factory. Here we use, in our data management concept, a so-called digital twin. A digital twin contains all the information that defines the characteristics and the behavior of a real asset. And an asset administration shell provides clear standards for data models and interfaces of such a digital twin. So it's very important to have an asset administration shell to describe this or to have the data of a digital twin. And the asset administration shells are, in my opinion, one of the most important concepts in the context of Industry 4.0. But originally, an asset administration shell is only a file. Therefore, we have implemented a so-called AAS agent server. And the agent server is containing a repository, you can see here, which stores the administration shell data. And it contains of an APCUA, application programming interface, to exchange data with other agent servers, with applications, or with other controllers. So we have a standardized data exchange mechanism based on OPCUA. To give you an idea how to use such an agent server, we can have a look on this picture. The identical agent server is built in every smart factory module. And the agent server stores the data of the local asset administration shells, the local data about the module, about the processes in this module. And applications, control applications, call these PLC services using this agent server. You know this already as a service-oriented production. This is realized with these agent servers. And with OPCOA, you can have an standardized data exchange within the module and with other agent servers in other modules. So additionally, we have a central edge server, and on the central edge server, there is also an agent server which stores asset administration shells with informations for the entire smart factory, for the workpiece carriers, for example, because the workpiece carrier are not module specific, they move from one module to another, so we have to store these data on a central point. And you have also applications here on the central edge server. And these applications are used to operate the smart factory, to visualize key figures you are interested in. And these central applications are using the data from the central asset administration shells in the agent server, or they can use or can read or exchange data with the local agent servers. And one important thing is that these agent servers, the applications, are embedded in Docker containers, though you can use them on every hardware platform you want. So you are very flexible in the usage of these functionalities. So, I come to the end of my presentation. I want to give you a short summary. At the beginning, I talked about the mechanical design, and there's important to realize a modular design with standardized mechanical and electrical interfaces. Another important topic is this robot-based multi-directional material flow to enable every sequence of value-added processes in such a smart factory. The second topic was the control technology. I have presented a decentralized, autonomous, and service-based control system. And we have seen that the deadlock avoidance is very important in the context of a smart factory, though you can handle this with a previous material flow simulation. And this is not only nice to have, it's really important to avoid deadlocks in such a high flexible production environment, because not everything goes straight ahead. The workpiece carriers are moving through the whole smart factory to find the suitable value-added module. It's much more complex than in a conventional production. And last but not least, the most important aspect is the data management. I have presented the asset administration shells, which provide standardized data models, the agent server concept, which enables standardized data exchange. And with all that, you can do a real-time analysis, more and more based on machine learning algorithms to optimize production and to predict, for example, maintenance needs. Currently, we are building up such a smart factory at the University of Amberg. You can hear some pictures about the current status of the construction work, and here some pictures of the structure of our smart factory. And finally, I would like to show you a video sequence where the material flow processes are visualized. This is the way the smart factory should work in future. You can see a lot of robots doing the material flow. There are also robots in the value-added modules to do the value-added processes. And of course, the robots are controlled with the SICI. So I come to the end of my presentation. If you are interested in smart factories, I would like to invite you to visit me and my team in Amberg. Thank you very much for your attention, and I'm happy to answer your questions now or during the next break. Thank you very much.
Thank you very much, Matthias. You've already invited them to ask some questions. Do we have any in the room for Matthias at all? Don't be so shy. Doesn't seem to be the case. I have one that a participant gave me before. He was a bit shy. So the research results that you showed, right? Can they? I mean, you mentioned conventional production facilities already, production systems. So how can you use these research results in these conventional systems as well?
Yes. The topics I talked about are not only suitable for smart factories. They can be used to accelerate the digital transformation also in conventional production systems. Though the concept of asset administration shells, this is a beginning to do the digital transformation, because data management is one of the most important things for future in a production system. As I told in the presentation, a lot of functionalities like optimization of the production, predictive of maintenance needs, such things are based on data. And so it's very important to have a standardized data model where you can read the data in a standardized manner. So you can use these asset administration shells. Then the OPCUA-based agent servers are very interesting also for conventional production systems. A material flow is not only helpful in smart factories, you can only use it to optimize your conventional productions. Also, most of these technologies are also suitable for conventional production systems, but they are needed to realize a smart factory. And additionally comes the multidirectional material flow, as I told, but the most technologies can also be used in a conventional production system.
Okay, thank you. And yeah, as you said, feel free to make use of the next networking break to ask Matthias any more questions you might have. Oh, sorry, Leila, that was quick. Yes, we have one at the back. Thank you. Just save me. And was there one down here as well?
Hello. Thanks for the presentation. You mentioned two things. One is OPCUA, so there's a companion spec, for example, for communicating between robots, as far as I know. On the other hand, there's the SRCI, or the administration shell. Those three standards, how far are they away from each other, or are they getting close? Would be interesting.
These are three standards, and it's very important for me to use, whenever it's possible, to use standards. Not to implement own proprietary solutions. If there's a standard, we use it. And SRCI, for example, is very interesting for controlling a robot by a PLC, but not all robot manufacturer supports this. That's not so good. I hope the robot manufacturers will do their homework in future to do this. The asset administration shell, it's a completely other topic. But they all work together to build such a smart factory. And OPCUA is well known, and we used OPCUA because it's a standard. Other data exchange mechanisms which are specified in context of asset administration shells are, for example, MQTT or REST. But OPCUA is a protocol, has a defined protocol. With MQTT, it's only in byte transfer, and you have to create your protocol by your own, and then you are not standard conform. So OPCUA is the industrial standard for data exchange, though we use it. And we use different OPCUA technology like client-server, publisher-subscriber. This is only possible. It's also possible with OPCUA, and it's a very strong protocol.
Okay, thank you. We're going to have to leave it there. I know there's a few more questions here and at the back, so kindly get in touch with Matthias afterwards, and I'm sure he's happy to answer them. Thank you again, Matthias Wenck. Round of applause.
Thank you.